Thank you very much for the kind introduction. It's a real pleasure to be here and present a little bit our work. So this is from a computer science perspective, looking at safety of deployment. I know some of the safety people will disagree with me what safety means, but I want to give you a little bit our perspective. I did ask last night Microsoft Copilot how this conference would look like. So I asked it to draw a colorful cartoon. And I think it's a nice kind of summary of how impressive AI is, and at the same time, how brittle, and sometimes it can be terribly wrong. For example, not getting the letters right here, trying to introduce us to something that looks like a living X-ray machine on stage here, and interestingly also trying to introduce an interesting trend where you have to wear your badge at the back. Not sure what that is about. But of course, I don't have to kind of make the case for AI has its potential a lot across various medical applications. I think we will hear a little bit more about skin later, but of course in assessing trauma, brain scans, breast cancer screening, retinal imaging, and all kinds of other applications. But I think what this session is about that it's not, we cannot just stop by assessing kind of performance of AI algorithms by looking at the classical performance metrics. That might be accuracy, that might be sensitivity, specificity. Those metrics are not enough to assess whether a model is useful and safe to be used in clinical practice. So what we argue is that there are many, many different perspectives to be looked at and heard. And I want to talk a little bit about some of those, trying to touch upon all three columns, but primarily with a computer science perspective, looking at the algorithms, and then also a little bit on biases and fairness. So this is kind of a diagram that we came up with at some point, saying that we need to shift a little bit also the research efforts from not just trying to build a nice AI algorithm, but to see what we can build technologically, what we can build around that AI algorithm. In particular, in terms of safeguards, can we put in mechanisms that allow us to check that the inputs are valid and compatible with the model? Can we do things and monitor and look at the outputs of a model? And can that help us to implement the model in a clinical workflow more safely? And then, of course, we have this important aspect of also trying to make sure that our models can be trusted, and that touches upon the idea of making sure that it works across the population where we want it to work. So I will rush through a little bit through all these different things. So just in terms of a little bit kind of definitions. So for me, robustness is what is the algorithm's ability to preserve its performance across variations in the input data. So it's very much focused on kind of what goes into the model. And what we would like to have, ideally, is some sort of neural eye examination that if someone gives us a model, let's say we are a clinical director who has seen a nice model being offered by a vendor and we don't quite know about that black box model and we want to assess it, could we do some sort of eye test on the model and examine how that model might perform, for example, across our different scanners that we might use in the hospital? So there are some ideas around this. Some of this is called stress testing, where we can take variations, perturbations of input, and we might do this in some simple way. For example, we could use chest x-rays and perturb the image characteristics and just see how the model reacts to these type of changes. I mean, these are very simple changes, so we can do things like change the brightness, change the contrast. It's all very much heuristic. But it is already useful to reveal some important differences maybe between models. So here's an example where we use some of those simple stress testing to evaluate two different models. And if you look here at those performance plots, the first column is the performance metric, so here measured as TPR and FPR rates on a test set. So a holdout test set where we get then some performance of two different models. These are chest x-ray models trying to confirm that there's no finding in a chest x-ray. And if you just look at the first column, so this is what you would normally do in terms of your holdout or external validation, you get some performance metrics. And there's almost no difference between the models. They have kind of the same, very close performance. If you then go from the left to the right, this is where we test the same model on different perturbations of the images. And you see that one of the models is actually much more robust to those types of perturbations and the other one isn't. So you wouldn't see that type of change in robustness if you would just look at standard kind of external validation, having real data and performance metrics. Here you can basically assess, for example, that this lower model is much more stable across these changes in image characteristics. So that might give us some kind of better insight into the model's robustness. What we are trying to do in the future, and this is linking up a little bit of work that was discussed yesterday about synthesizing images specifically. So this is some work where we build generative models that can alter very with a very targeted perturbation or transformation or intervention, we say sometimes, change an image to look like something that we want it to look like. So for example, we can take a real chest X-ray image as an input, which might have some characteristics, like this was taken from a male with race black, age 45, and no finding. And now we can make interventions with a generative model on that chest X-ray that hopefully gives us realistic what-if images. How might that image look like if there was actually pleural effusion present? We can then also use that type of generative AI to go back to our problem of robustness against, for example, changes in the input, and synthesize images how they might look like if they had been taken with a different scanner. So here are some examples coming out of our model where we synthesize digital mammography going from one type of scanner to another scanner. So we're synthesizing or simulating how that image would have looked like if it would have been taken with a different scanner. The same we can do for chest X-ray. And that, again, allows us a much more targeted and hopefully realistic way of changing image characteristics and then measuring how a model might react to these type of changes. Another important aspect is on the input side is actually the data that goes into a model for training, but also for testing. And what we did find, so there's some work with Chiron Medical where we looked at very large data sets of many hundreds of thousands of images that you might want to use for training. But of course, your model shouldn't be trained on data that isn't of sufficient quality. Right? For example, you want to make sure that your model kind of is not trained on data that is just corrupt. The issue is that those models that are trained on very, very large amounts of data, there's no way you can do manual quality control. You can't go through all these images one by one. So again, we're using an AI system, actually a very, very simple one. It's an autoencoder where you parse in an image and it kind of learns a low-dimensional representation, has to reconstruct that image. And it can only do this if the image is of sufficient quality, if we had carefully kind of designed that model. So by looking at what we call the reconstruction error, we can automatically detect images that are somewhat unusual. So either there's maybe some metal in there, or maybe there's even here a hand that came across the X-ray source, or some spot magnification that maybe we didn't want to have in our model, or even corruptions. So these are type of automatic quality control systems are also really important for kind of our side of the what's going into the model, the input safeguards. So now I want to talk a little bit about the output safeguards. What can we do when we look at the predictions of a model? So again, a quick definition, what is reliability? For me, it is the question whether we can trust the algorithm's output. And ideally, an algorithm would have the ability to raise a flag saying, I'm not certain here, please ignore my prediction. So the dream would be to have that system where you have a model that does its classification and you can trust the decision when the confidence is high. And then there is a separate path that actually looks at the model output, assesses its confidence. Maybe the model can do it itself. Maybe you need another model looking at the outputs. And then you have some idea of confidence score. And you might want to reject the model's prediction. And maybe you want to use a referral system and give it to a human. So we looked at the literature. We looked at a lot of kind of technological solutions to automatic failure detection. And the bad news is they don't work. So at the moment, we don't have very good ways of automatically detecting when a model is wrong. And that goes back to my very first image. AI models tend to be confident in their predictions, sometimes regardless of whether they are right and wrong. And that is a problem with miscalibration of AI systems. Of course, there has been a lot of work on that, and hopefully in the future we have more reliable system. But at the moment, I believe we need other ways of making sure that we, despite not AI systems always being super reliable, they can still be very useful, and what can we do in terms of safety nets putting around there. So again, some work with my colleagues at Chiron. Of course, in some settings, you can just think about a very clever workflow. Integrate the AI system in a way that it is safe, but also effective in terms of helping you to reduce workload, making sure you detect the cancers you need to detect. So here are 3 different workflows that we assessed. The first one is just human-based. You have double reading workflow in screening. Then you have, I think that was probably one of the first that people suggested in the UK, get rid of one of the human, put in the AI, save workload. The question is what happens if they disagree? So there's another workflow, and I think this sometimes goes back to the question of what is actually the best way of having AI and human collaboration. What if, whenever they disagree, reader 1 and AI, you actually bring back the second human? Now, what does that mean operationally? What we could show is that, of course, you save the most in terms of workload if you just replace one human. But you can still massively save in this scenario where AI and the first reader will very often agree, and only in some cases disagree, where you bring in the second reader. And it also turns out that this is beneficial in terms of the arbitration rate, so the number of cases that will go to arbitration. So just one example of one way of just thinking a little bit, what could we do differently? How could we integrate AI? And there isn't always just one way. There are many ways. Gerald will be very familiar with that one, where the AI is actually now being acting as a safety net. So you have our standard workflow. 2 humans look at every scan, and then there's an AI-assisted reader that looks at every scan at the back and looks at the ones where the human said no, but where the AI is confident that actually there is something that they might have missed and you add an additional review. Again, another way of integrating AI. It has completely different consequences on your workflow, but maybe you can combine the 2 and maybe get the best out of both human safety nets and AI safety nets. So the other problem is when we, and I alluded to this a little bit earlier, that AI systems are not always very robust, especially when it comes to changes in the input data, and the data is different from what it has ever seen before. So when there are drifts in the data, for example, you have trained a system on one type of scanner, and now your hospital replaces the scanner, what happens with the AI system? We know that AI systems are susceptible to that type of change in the input data. Here's an example where we explicitly trained an AI system on just one type of scanner with and that achieved a certain type of performance, right? So here we said we want a certain sensitivity specificity trade-off, and now it's being tested on a scanner that it has never seen before. Interestingly, what happens, and you can see this from these metrics, the model is still able to separate cancer and no cancer, but at a different operating point. So the threshold that was optimized on this scanner doesn't apply to this other scanner. And if you look at the output, so this is going to the point of monitoring output distributions, if you plot the output distributions of the model, you basically see they are shifted. They are not wrong, but they are just shifted. So the model is differently calibrated in this case. And we came up with a solution that we call autocorrection, where you kind of apply a transformation to the outputs, and you can go back to the performance that you wanted. And that works really well. So we tested this in different scenarios. For example, what happens if you slowly transition to a new scanner at your site, or you add a new scanner? If you don't do anything and you just let the AI model run, you start drifting in terms of performance, in terms of your sensitivity specificity trade-off. And with our autocorrection method, we could basically see, so these are the orange lines, that it detects very quickly that there's a problem, and with the autocorrection on the model outputs, it goes back to the expected performance. And the same happens, and this did happen actually at some point, where we saw that a vendor of a scanner applied a software update, and that made the images look slightly different. In their perspective, it made them look better, but the AI model kind of was susceptible. And again, with an autocorrection technique, you can immediately detect this, and instead of then operating on this wrong performance trade-off, you go back to the expected performance. The big issue is with autocorrection is it safe to actually do autocorrection on your models? And how do you know that you can change the model outputs? Because a change in model outputs might also just come from a change in your patient population. Or you have something like COVID happening, screening programs being paused, people come back, and suddenly you have an increase or spike in cancers, right? Because people have not gone to their regular screening appointments. So you might have population shift or prevalence shift. There are all kinds of different data distribution shifts that you have to kind of disentangle and identify. So it is actually not safe to apply our autocorrection method blindly. What you need to do is you need to monitor what's going on with your data distribution. So you need to detect whether there's shift. And that's not enough. So that goes back to, I think, what Kevin said about root cause analysis. You need to then find out what was the root cause of that shift. And there are many different shifts that can happen. So covariate shift is kind of encapsulating anything that happens on the inputs. Prevalence, of course, is happening when you have a change in disease distribution and so on. So you need to identify, and one way of doing it from a technological point of view is open up the black box, look inside, and that's what we are doing here. So we are monitoring not only what's coming out of the model in terms of predictions, cancer, yes, no, but also the feature distributions itself. So you have to slice up the model and look at the distributions that are happening on the kind of feature representations of those images, and putting it all together into some more or less clever logic, you can then separate out what type of shift might be present or not. And if you, for example, then work out that it's covariate shift only, you might be saying, okay, actually we can apply autocorrection in that case. So generally the point here I want to make is we really need to kind of start better understanding what our data generating process is. How did the data come together? Often we have a very narrow kind of focus of we have an image and we have some prediction targets. But what we need to do is we need to kind of look at the bigger picture of how the data came together, because that allows us to not only identify, but also then talk about mitigation strategies for all types of shift. Some of those shifts are not something that you can actually do much about, but you still need to know about it. And some of those shifts you can come up with technical solutions and do something about it. So the last thing I want to mention, and I'm running out of time, but I really want to highlight a little bit the work on bias and subgroup performance analysis, because I think it is so important, and it has been discussed a lot already yesterday, but it's really, really tricky. So you will find reports in the literature that say AI is biased and has been shown in different kind of settings, that sometimes it seems to do underdiagnosis for certain subgroups, and all these kind of issues. And at the same time, we know that medical images encode a lot of information. Other than the disease, it encodes ethnicity, it encodes age, it encodes biological sex, and all kinds of other protected characteristics. So a model might actually start using that type of information that it can extract. How do we know? And this is in particular concerning, or maybe something to think about in the context of foundation models. So these are large-scale models trained on millions of data, where the idea is then you use that foundation model to build a downstream application. Right? So you could pre-train a large foundation model, and then downstream application could be chest X-ray disease detection, breast cancer detection. You basically fine-tune that model. Now, those models are available already. So Google has one, many others have one that you can download and use, and they suggest you can build your applications downstream. Now, one thing that we tried to do is to find ways of, from a methodological point of view, assessing whether a model is biased. So what we did, we trained our own chest X-ray disease detection model, and we compared it to a model that is provided online, a so-called chest X-ray foundation model. And here we're using techniques, again, opening up the black box, looking inside, and looking at feature distributions across subgroups. So what you're seeing in these colorful plots is that we have a column where the features are separated by disease. That's what the model should do. And then at the same time, we can look at, are those disease features also separating other characteristics? So here we can look at biological sex and race. This is our baseline model, and this was the Google Foundation model. And what you can see if I flick forth and back, that there's a shift in those distributions. So we can detect this, even without knowing anything about the model performance yet. If we then compare this to actual model performance, we find that those shifts have actually introduced, or can also be associated with lower performance across subgroups. So this is absolute performance. So this is just subtracting TPR and FVR. You see all those gray, orange, and blue models are the foundation model. They are on general performing worse. But in particular, if you compare per subgroup to the average performance, you see very clear disparities across subgroups. And one of those issues was that those models were trained on very large amounts of data, and they say diverse and heterogeneous, but we still don't know much about it because that data isn't accessible. We don't know exactly what's going into these model trainings. But with techniques like this, at least we can try to open up the box and have a better look at what might be going on. So our vision for safe deployment is actually to do this. Have an AI model that does a very important clinical task, but put safeguards around this. So have things like automatic image quality control, drift detection, auto-calibration in the future we will have, and of course bias detection. So just very quick advertisement for Chai. Gerald has already done this. If you want to join the causal revolution in healthcare AI, please join our community, and I leave it here. Thank you.